Alright, hello class. In this video we're going to be starting on the next module, which is on multiple integration. And we'll start specifically with double integrals. Okay, but mechanically, I think double integrals, triple integrals, multiple integration, you all could probably do without much instruction, just the calculating the integrals part based on what we already know. Okay, and I can show you that with an example. Alright, so for example, if I just threw this particular integral at you, say the integral from 0 to 1, integral from 0 to 2, of 6 minus 2x minus y dy dx, just based on what we know about partial derivatives, you may just start by thinking, oh, okay, I have a dy. So on this inside integral here, we'll just integrate with respect to y and treat x like a constant. And that's exactly what we're going to do. We'll ignore the dx stuff here. We always work inside out. Okay, integral signs you can think of them as parentheses, right? The integral sign with its d whatever, dy, dx, dz, whatever. Those are grouping symbols, like parentheses. So this will be integral of 0 to 1. All right, and now I'm going to integrate this stuff with respect to y. So the integral of a constant with respect to y will be 6y. Negative 2x is also a constant. So the integral with respect to y of a constant is y times that constant. Right? So I have 6y minus 2xy, then minus the integral of y is 1/2 y squared. Okay, and we're going to evaluate this from, I'm just going to write this y going from 0 to 2. Okay, and now we do our fundamental theorem of calculus step, where we plug in the 2, plug in the 0, and subtract. Okay, so it'll be 6 times 2 minus 2x times 2 minus 1/2 times 2 squared. So there's plugging in the top. And then plugging in the 0, you'll note we can do that quickly. Okay. All we're doing is subtracting by 0 there. Okay. Oops. There we go. Now, we'll simplify this. We'll have the integral from 0 to 1. That'll be 12 minus 4x. Then minus, that will be 2. Okay, so we'll end up with the integral from 0 to 1 of 10 minus 4x dx. And now, it's just a calculus 1 problem. Right, since we've gotten it reduced down to an integral of a single variable. Okay, so we just integrate this. This integral of 10 minus 4x dx will be 10x minus 2x squared. And we will evaluate that by the fundamental theorem of calculus by plugging in 1 and 0. Okay, so we get 8. Okay, so that is essentially how this works. If this had started with an x on the inside, instead you would have integrated with respect to x and treated the y like a constant. It essentially works as the opposite of partial differentiation. All right, which is essentially what it is. In a y integral, we integrate with respect to y, treating the x like the constant, or vice versa. So, given that, mechanically, right, this isn't going to be much new. Now there are a couple of things that, will change things up a little bit, all right, that we'll have to look at. U substitution gets a little funky. Okay, but what I really want to focus on in these videos is more about the setup, because once the integral gets set up, you just crank through it like you normally would. Just works how you would expect it to. It's the setup that I think really is really important here. Okay, so the main big question is, well, what is this? Right? What is this integral? Right? This double integral, what does it give us? Okay? Well, to answer this question, and again, I'm sure I sound like a broken record at this point, but let's recall what the Calc 1 integral was. Right? And we're talking about definite integration here. But if we had a function f of x, and we were looking at it from x equals a to, let's say, x equals b, okay, what the integral of f of x from a to b was ended up being the area between the curve and the x-axis. Right, so it gave us the net area between the graph of x, or graph of f of x, excuse me, and the x-axis. Okay, and how we got this, if you remember, is we would take our region A to B, our line, and split it up into a bunch of equal pieces. Okay, and each piece would be, say, delta x, and we would make rectangles under the curve of f. Okay, and so the sum of these rectangles would approximate, right, would approximate the actual integral. Okay, so we would maybe split it up into n equal pieces, and what would end up happening is as we let the limit as n goes to infinity, which is the same thing as letting delta x go to 0, this sum, right, would become an infinite sum, but the a's themselves would get smaller and smaller and smaller, and we would actually get an equality equal to the integral. Okay? So that's essentially what we did. We would take each a sub k would be, say, the height. Let's say it's f sub k. So f sub x sub k, okay, times delta x. So each one of these, delta x would get smaller and smaller and smaller, but we'd get infinitely more and more of them. Okay, and we would sum all these up, and that would give us the definite integral when we were finished. Okay, so when we instead think about what's happening with a double integral. Okay, double integrals are often generally written like this: two integral signs together over an r, f of xy dA. Okay, well, what is this? Well, imagine we have the surface z equals f of xy. All right, so let's say this is the graph of our surface. Looks something like this. Okay, and here we have the region R on the xy plane. Okay, it could be anything. It could be a rectangle, it could be a circle, triangle, whatever. Okay, and if we map this whole region up to where it intersects with the surface. Okay, who knows what it might look like. So here, the way I've drawn it, it looks kind of like we have a box with a funky top to it. Okay? What we've created here is a solid. We'll call it S. Okay? And what this double integral gives us, it's the volume of this solid. Because what we do is just like with the areas from before, right, where we split this into rectangles, what we do is we split this region into a bunch of boxes that are all the same length and width, right? So if we zoom in on one of these, okay, we'll have a delta x and a delta y. Okay, and together, well, delta x times delta y, we call delta A. Okay, and then for each of these, we make a box. So I'll zoom in over here. Okay, so here over each one of these little boxes, or each one of these little squares, right, we make a little box, which will be a delta x by delta y by whatever height we choose. Now we can choose the f value, like the z value right here on one of the corners, right in the middle, wherever we want. It really doesn't matter at the end, because what we're going to do is shrink these down to 0. So we might want to choose the one right in the middle or in the corner here. It doesn't really matter, because eventually they all come together to be one. But the volume, right, of this little box is going to be, well, it's base times height, or base times width times height. So it's our height times delta x times delta y. Okay, so this is also known as delta A. All right, so when we sum all of these up, all of these v sub k's, say if we have n of them, we're going to have like lots, right? So we have to go through the y's and the x's. Okay, so let's say we have j going from 1 to n. All right, and k sub j, so we could do j here. Okay, just so we count in different letters through the x and the y. These all together are going to give us approximately the volume between the surface and the xy plane. Right, and just like before, as delta x and delta y go to 0, we get equality to the double integral over r f of xy dA. And again, dA is dx dy or dy dx. The reason we use dA is because order is really important when we start doing this, and we will get into that. So anyway, the whole point here is that the volume of this surface that we've created here, okay, can be calculated by the double integral. Okay, so if that feels like a little too abstract for you, don't worry too much about it. What really matters is that what we're doing is we are creating a surface over the region R with height given to us by the surface F. Okay, so we're typically always looking at flat bases. There are ways to change what the base looks like, but that would just be taking that one height and subtracting off the other height, just like you do it with standard integrals when you're talking about areas. Okay, so we can complicate this a bit. What's important is how these are set up, right? There are two ways that we typically represent R. So you might be wondering what's going on here. So R is the description of the region. So I'll just say the region on the XY plane. And it determines the limits of integration. Okay, and it does so in the following way. There are two ways that we can want to orient our regions. Okay, so there are two ways we can orient R. Either we can think of it either as bottom to top or left to right. What this basically means is how we're going to set up the integral. Is the x integral on the inside or is the y integral on the inside? Okay, so bottom to top is how we usually think about this is how we usually think about graphs, right? Which is basically y equals a function of x, right? That's how we usually think about graphs. So usually when we're doing a bottom to top approach, we're looking at a y equals f of x and a y equals g of x. All right, now this is going to be really familiar from Calculus 2 when you had to reorient some integrals in order to do solids of revolution or do things in terms of y. Because when we think about it in terms of left to right, that's what we're talking about here. This is the flipped version. Right, so this is opposite of how we usually think of it. Left to right, it's always like an x equals capital F of y, or x is equal to capital G of y. Okay, so let me explain what I mean here. If the book kind of does this differently, but I prefer to think of it this way, because if you always think about your integrals in terms of orienting them either top to bottom or left to right, it's really going to simplify your life, at least in my opinion. And that's how I set things up when it comes to like integrals for solids of revolution or for areas or what have you. Even in Calculus 2, I always think about it left to right or bottom to top. Okay, so here's what I mean. Okay, so suppose our region looks like this. It's the region trapped between the graph y equals f of x and y equals g of x, and we're only looking at x is going from A to B. Now, I put an intersection here because sometimes it's where they intersect. Of course, sometimes it's not. If they don't intersect, you're going to get a vertical line as one of your sides, and if they do intersect, you just get this point. Okay, so this is let's say our region R. Okay, so if this is our setup, then the volume, okay, of the solid S between f of x, y, and R is, well, always it's this double integral over R of f of x, y, dA. However, if this is the way that we talk about it, okay, it is going to be All right, we'll have the double integral, and we're going to put the y integral on the inside, because what we want is the inside integral to give us y going from g of x to y going to f of x. Okay, f of xy dy dx. Right, and then the x integral goes from a to b. All right, so what is happening here is we're actually going from the bottom of R to the top of R. Okay, so here's the bottom of R. Okay, so here's the bottom. And here's the top. Right, because as we go from A to B and we map upwards, the first one we hit is this g of x, and the second one we hit is this top function. So if we want to orient it this way, this is how we are going to do it. And then for x, all we're doing is mapping out how far along we go on the x-axis. Okay? So I will often write this in this way. I'll say, okay, this is the integral from x going from A to B, and y going from the bottom function of x to the top function of x. Right? dy dx. Okay? So here I just switched the colors out. And this, we want the y integral on the inside. Now, whenever we do this, we always want the outer integral to always go from constant to constant. That has to happen, right? So the outer integral always goes from constant to constant. Now, let's say it's the other way around. Okay, let's say our region isn't defined in this way, but it's more easier to define it as x equals something. Okay, so instead, let's say we have the region R that's bounded by the function x is equal to f of y and x is equal to g of y, and y ranges between c and d. Okay, so in this case, the volume of the solid between f of xy and R is still the double integral, except now we set it up in the opposite order. Here it's going to be y on the outside going from C to D, while on the inside we'll have x going from the left side, which is G, to the right side, which is capital F of y. Right? And then we'll have f of xy dx dy. So in this case, it's the x integral on the inside. Okay, and like before, what we're doing is, also like before, I had one side have an intersection and one side not. Right, so I mean, it doesn't always have to look like this, but just to show what's going on there. Anyway, okay. Once again, we are thinking about this region in terms of its left side and its right side. Right? Because if you map from the y-axis over, right, to the region itself, left to right, the first thing you hit is G, and the second thing you hit is F. Okay, and then once again, all the y limits tell us is how far along the y-axis we go, from C to D, just like we did before. Okay, so like before, I will often write this as the integral from y equals C to y equals D. Then instead of, this is usually how the book writes it, but I tend to just think of it as x goes from left of y 2x equals right of y. F of xy, this part doesn't change. Then it will be dx dy, and we will do the x integral first in this situation. All right, now I'm certain that this seems very abstract and hard to wrap your head around. It's not surprising. This isn't the easiest stuff in the world when you first start playing with it. Okay, so I'm going to start moving to examples now and showing like why we might even want to care about this situation, right? Because there's this one, right, which makes sense. That's how we're used to thinking about regions on the xy plane. So you might think, well, why don't we just always set it up that way? And well, the answer tends to be because integration is messy, right? Because there are certain forms of integration that are just flat out impossible or just really extremely difficult depending on what direction you're trying to go in. All right, so let's just start with a simple example and we'll start moving from there. All right, so let's find the volume of the solid bounded by the surface f of xy equals 2xy over the region R given in the graph here, which is this little triangle with vertices at the origin 1, 0, and 0, 1. Okay, so like I said, I'm trying to start fairly stress-free as much as we can. Okay, so the volume is going to be the double integral over R of f of xy dA. So now we get to decide which way do we want to orient our integral. And my advice is whenever you can, do bottom to top. Okay, that's just the nicest way. So if we're going bottom to top, so if I think about the edges of my graph, well, if I'm going bottom, the first thing I hit is this line here. And the second thing I hit is this line here. So this is going to be our bottom. This is going to be our top. Okay? So when we set up our integral, right, I'm not going to worry about the outer integral to start with. It's always y goes from the bottom function to the top function. So we need to figure out what these functions are. Okay, now the bottom shouldn't be too difficult. This is a horizontal line. So that just to me looks like y equals 0. Okay, so we can just put that in y equals 0. Okay, and then for the top function, well, this is a line. And it looks to me, well, it's got y-intercept 1 and slope -1. So this looks like the line y equals 1 minus x. Okay, so that's our top function. So on the inside of our integral, y is going from 0, which is the bottom, to 1 minus x, which is the top. Okay? Now, what we want to know is, what does x go between? Well, x, you know, our region stops here and stops here, right? So x can't be any negative value, and it can't be any positive value greater than 1, so it's actually trapped in this region here, which is 0 to 1. Okay, so x goes from 0 to 1. Okay, so that's what the outer integral is always doing, is just deciding, okay, how far do we go out on the other variable? Okay, now our f of xy, that's of course 2xy. And then we're going to do our y integral first and our x integral second. Now, what I want to specify here, notice how I'm being very specific about writing y equals, x equals. The more variables you have going along and you're trying to, you know, plug things in using the fundamental theorem of calculus and working through integration and all that, it can be really easy to mix up what variable you should be plugging into because, well, it might sound a little silly, but we're so used to plugging things into x that we might accidentally plug these into x when we should be plugging them into y. Okay, so that's why I'm being very explicit here. You'll notice if you look in the book, they don't do this. Okay, this is more my way of keeping track of what's going on. Okay, all right, so we'll leave the x limits alone, and here we're just going to integrate just in terms of y. Okay, so for this first example, I'm still going to go through this fairly slowly. We're going to integrate with respect to y. We're going to treat x like it's a constant, so we're not going to mess with x just yet, right? So we're just dealing with this integral here. Okay, so the 2 is left alone, the x is left alone, and then the integral of y is 1/2 y squared. Okay, so the 2's will cancel, and then we're going to evaluate this, and this would be our fundamental theorem of calculus step, from y equals 0 to y equals 1 minus x. And then on the outside we still have our dx. Now, I know it's very common for calculus students to forget to write their dy or their dx or whatever. This can be a really big deal here because this is what tells you what order you're integrating in, right? You're going inside out. If you don't put this, the reader doesn't know what direction that you're actually integrating in, like what order. And order, as we're going to see, is extremely important. Okay, so this step here, all I've done is just clean this up a little bit. And so when we do the fundamental theorem of calculus, well, when we plug in the 0, we'll just get 0. Okay, when we plug in the 1 minus x, right, we're going to be plugging it in to the y squared. Okay, so that will be our fundamental theorem of calculus step. All right, so we'll get the integral from x equals 0 to x equals 1 of x times, here we go, we're plugging in the 1 minus x squared. Okay, and then we'll have, whoops, actually let me actually write it out, minus 0, just to be really explicit here, and then dx. Okay, so the reason I'm going a little slower through this is actually I'm pretty sure this is the first example we've seen of putting variables in the limits. So I think it's advantageous. Okay, so now we just have this integral. I'm going to drop the x equals here because now we're just going to have an integral in terms of x. So if I FOIL this out, best way to go about this one, we'll get 1 minus 2x plus x squared dx. And so we'll have the integral from 0 to 1 of x minus 2x squared plus x cubed dx. And this now is a, well, this is a Cal 1 problem now. Okay, so hopefully this isn't too crazy from here. We'll have 1/2 x squared minus 2/3 x cubed plus 1/4 x to the 4th, and we'll evaluate this between 0 and 1. So for the fundamental theorem of calculus step, we're going to plug in 1s, so we'll have 1/2 minus 2/3 plus 1/4. And we're going to subtract away when we plug in the 0. I always write it just to make sure I get it because it doesn't always 0, right? It doesn't always go to 0. All right, and that comes out to be 1/12. 1/12. Okay? All right, to show what is going on the graph here, here is the graph of the surface z equals 2xy. Right now, here is the region on the xy plane that we're actually looking over. Okay, now if we just look at here is the line, and if we map that up to the surface itself, we see this sort of shape going on here. And if I just restrict everything, so let's do that, there we go, and this is essentially the shape we're looking at. Pretend this part is filled in as well, but what we've just found is the volume of this little shape here. It almost looks like what do they call those little horn, like the horn of plenty or whatever. It's kind of what this little guy looks like. But yeah, that's what we found. We found that the volume of this solid here filled in, right? So if we were to fill this in with water, we could fill it in with 1/12 whatever our units of volume is there, whether it's gallons or what have you. Okay, so that's just graphically what it is we're doing. All right, so I'm going to put a cut in this particular video because the this topic is a pretty large one, so I don't want this to be like almost a 2-hour video or hour and a half or anything. So we'll come back in the second half and look at examples where we need to split, or not split, but I'm sorry, swap the order of integration. So that is why we need to be able to set these up in different orientations. Okay, so I will catch you all on that video.